Okay, this is Unit 6, Chapter 22. We're going to talk about power. So first of all, this is a diagram in the book that's very helpful. This is an oversimplification of basically how we get our energy. So you have, waterfall, for example, which would be potential energy, gravitational potential energy. And as it falls, it moves this, turbine or water wheel, and it turns it into kinetic energy. So we have the conversion of potential energy to kinetic energy. Which then spins this generator, which we know is a magnet that then can push charges. And those charges can then, turn a motor, which can do something. So what you have is potential energy of the water being converted into electrical energy through a generator, and then that electrical energy turning a motor, which does work for us. Now, obviously, some of that energy is lost in the form of thermal energy. So you have heat from friction and things like that from the moving parts. And the idea is to minimize this thermal energy to have a more efficient system. So things like, the invention of a wheel bearing in here or a ball bearing to minimize the friction and therefore minimize the amount of heat that's given off, it was a game changer. Brushless motors would be another example of something that obviously minimizes the friction and therefore increases efficiency. So the equation we're going to use for power, we've already used this in the lab with wind turbines, but power equals current times voltage. This poison ivy is an easy way to remember it, but it's on our formula sheet. This is going to be the most helpful formula to use to determine power. If we have both current and voltage, we can easily calculate the power in watts. So here's a perfect example then. Let's say we have a 6-volt battery and we have a current of 0.5 that it's able to deliver to an electric motor. What's the power? Well, power equals current times the voltage. So we have a current of 0.5 amps, we have a voltage of 6, so that'd be 3 watts. And then from there, for part B, it says if the motor runs for 5 minutes, how much electric energy is delivered? Well, we know that a watt is a joule per coulomb, or another way to look at this is power equals energy over time. So we have the power is 3, and we also have the time, so you can just use this formula here if you want. The power is 3. We're looking for the energy E, and the time we have is 5 minutes, but we do want to convert this to seconds because we know that our units have to be in things like joules, coulombs, seconds. So 5 minutes, we're going to convert that by multiplying 60 seconds are in 1 minute. So we want to multiply the 5 by 60 and then multiply it by both sides. So the energy we get ends up being 3 times 5 times 60, which is 900 joules of energy. Okay, the next thing we want to talk about is resistance. Resistance is something that restricts the flow of current in a circuit. So, the word kind of gives it away. It shouldn't be hard to remember. But there are some things that affect resistance that aren't so intuitive. One thing is length. Resistance increases as length increases. So if you're using an extension cord, you might have found this before, that if you have too long of an extension cord and you're using a device that requires a decent amount of power, you might trip a circuit, for example, or that device might have a hard time running because there's too much resistance in the circuit. A way you can make up for that is by looking at the cross-sectional area. If you have a thicker wire, that's going to decrease the resistance. So if you have a thinner wire, it's going to increase the resistance. So if you want to run a cable a long way, you're going to need to make it thicker. Temperature is also something that affects resistance. Resistance increases as temperature increases. You might hear power lines in the summer kind of buzzing above your head. And as it gets hotter, you might hear that buzzing a little bit louder. But there is resistance increases as temperature increases. And then the type of material, we've talked about this a little bit. There are some materials that are better conductors, and therefore, resistance is affected by that. So resistance increases in these elements here, and silver and copper are good conductors and therefore have low resistance. Okay, this is probably the most important relationship of the unit. I like to write it like this: V equals IR. This is Ohm's law. And it's going to be the most simple relationship that we've had all year long, probably. It's a direct relationship between voltage, current, and resistance. So a couple quick examples from these circuit diagrams here. Then if you have a 6-volt battery with a 30 ohm resistor, it's going to allow 0.2 amps of current if you use V equals IR. If you have a lower voltage now, you're going to end up with a lower current, obviously. And then if you had the same voltage you started with, but you increase the resistance now, you're also going to have a lower current. So keep in mind that we always hook up current probes in series. So here's a circuit diagram then that has a battery, a switch, a motor, and a potentiometer. We're not going to use potentiometers a lot in this class, if at all, but they are used quite a bit. They're just variable resistors, so they're resistors that can change. In fact, I believe that new cars, use variable resistors for things like the gas pedal, instead of actually having a mechanical setup that allows for, as you press the pedal, more and more gas comes in. Now, as you press the pedal, the resistance of a circuit changes, which then allows the computer to tell the car to deliver more gas to the cylinders. But here is the circuit diagram then. The battery looks like this, switch looks like this, a motor looks like this, a potentiometer looks like this, and the flow of current is given away by this arrow right here. Here's some more. Here's the important ones. Conductor is just going to be a line with a wire. Switch is going to look like this. We probably won't use fuse as much, but they look like this. Capacitor will look like that. We won't use inductors at all. Potentiometers we won't use, but they look like that. We will use resistors quite a bit. A lamp, we might put those in our diagrams. We will use voltmeters and amp meters like we already have. Battery for sure. And we probably won't use a DC generator at all in our circuits for now. Okay, let's do another example then of current through a resistor. Let's say we have a 30 volt battery and a 10 ohm resistor. What's the current? Well, we can just use V equals IR for this. We have a 30 volt battery. We're looking for the current. We have a resistor of 10. So if we divide by 10, we get a current of 3, and that'd be amps for current. Now, speaking of current, the book points this out, which I think is important. Current is actually what is the dangerous part. As you remember, our Van de Graaff generator created about 100,000 volts, which is a really high voltage. So we have a really high voltage from our Van de Graaff generator, but there's just not that many charges, so there's not that much current. So you basically, have a lot of resistance in that system, so to speak. But when we do get higher levels of current, that is the dangerous part. So current as low as 1 milliamp can be felt as a mild shock, which is probably about what you guys were feeling with the Van de Graaff generator. 15 milliamps can cause loss of muscle control, and 100 milliamps can be too much for you to handle. Okay, the next thing you want to know is parallel and series connections. In parallel connections, current has a choice of which path to follow. So for example, in this circuit diagram here, current can choose to go through this resistor or through this voltage probe or voltmeter. In a series connection though, current only has one path to follow. So in this circuit, the current is going to have to go through this resistor and then through the current meter. And if you remember from our lab that we've done already, we always hook up the voltage probes in parallel and the current probes in series. And that's because we need all the current to go through the current probe in order to read. With a voltage probe, what it is, it's actually just a really big resistor. And so it restricts most of the current takes the path of least resistance. So most of the current is going to go through this resistor here. A very little bit will go through here. And using that very little bit of current, it just uses V equals IR. So it knows the big resistance of that resistor. It can determine how much current's going through there and therefore determine the voltage across this resistor. Okay, we talked about power. Power is IV, but we also can rewrite that formula different ways if we use some simple substitution. So we can say that power is I squared R as well, and we can say that power is V squared over R. These are two different ways to represent power. And we can use these formulas in situations where we have voltage and resistance or resistance and current, for example. Some other formulas that are on your formula sheet is for thermal energy. So same as the formulas we have for power, only now we can just rearrange it, right? Because power equals energy over time, for example. So just multiply both sides by time, and you get this equation, which we already had. Same thing before, power, we had power equals I squared R. It's supposed to be squared. Now, power is energy over time. So replace power with energy over time, multiply both sides by T, and you get this formula. So that's where these formulas come from, but they are our thermal energy, which is the power dissipated multiplied by the time. So let's look at an example then. A heater has a resistance of 10 ohms, so we're given the resistance. We're also given the voltage is 120, and we're asked about power. So we're going to look at a power formula that involves voltage and resistance. That would be V squared over R. So we have 120 squared over 10, which gives us 1,440 watts. And for part B, what's the thermal energy supplied in 10 seconds? Well, keep in mind that's power, which equals energy over time. So we have energy over time equals 1440, and we can multiply both sides by time in order to get the energy. The time is 10 seconds, so multiply both sides by 10, and just add a 0 here, and you get 14,400 joules. Keep in mind that units are important, so this was watts, which was joules per second. And then when we multiply both sides by seconds, the seconds cancel and we get joules, which is what we want our units for energy. Okay, the last thing you want to know, or second to last thing, is a superconductor is a material with zero resistance or close to. Obviously, if there's zero resistance, there's no restriction of the current, and power dissipated in the conductor is given by the product IV, so it can conduct electricity without any loss of energy, which can be very, very useful. And if we could find a way to make cheaper superconductors, obviously we would benefit greatly from that. Next thing is a kilowatt hour. You need to know what this, we've talked about this. A kilowatt hour is 1,000 watts delivered continuously for 1 hour or 3,600 seconds. So if you just do the math on that, you have 1,000 watts, which is 1,000 joules per second, times 3,600 seconds. The seconds cancel, and you get 3.6 times 10 to the 6 joules. So a kilowatt hour is a unit of energy, and all it is 3.6 times 10 to the 6th joules. All right, let's try the homework, and hopefully this helps.